In this video, I want to take a look at a theorem that essentially says what we've been doing with series solutions is legit. And then I want to take a look at some things about how we can determine at least the size of the interval of convergence of the solutions. Okay. So, first of all, the definition. X0 is an ordinary point. I think we may have already sort of said an ordinary point. My impression is an ordinary point was a place where p of x is not equal to 0. However, it's a little more than that. So an ordinary point for this differential equation is a point where q divided by p and r divided by p are analytic. That is, they have Taylor series centered at x0, and the radius of convergence is bigger than 0. You can always set up a Taylor series, but it might be only convergent at that point. The interval of convergence is, 1 point. This is saying that no, there's a bigger interval than that where these things are convergent. So an ordinary point is when q over p and r over p are what's called analytic. Now notice that's how we generally write the formula anyway. We would divide by this p and have a 1 out in front of the y double prime. So the function here and there have to have Taylor polynomials that have intervals of convergence of non-zero length. Now, theorem. If x0 is an ordinary point for this differential equation, then the general solution can be found as a power series and split into two power series, a0 times one power series plus a0 times another power series, where those two, y1 and y2, are analytic series at 0. That is, they have Taylor polynomials at x0, which have intervals of convergence longer than length 0. And those two form a fundamental set of solutions for the differential equation, so that this is indeed the general solution. And we can also say that the radius of convergence for these two is at least as large as the minimum of the radius of convergence for q over p and r over p. Okay. It might be longer, but it's at least no shorter than the minimum of those two radii. So let's take a look at an example here. Here is a differential equation. P is 1 plus x squared. Notice 1 plus x squared is never 0. It's an upward opening parabola that has its vertex at 0, 1, so it's already up 1 and it opens upward. So this is analytic everywhere. So in particular, it's analytic at x equals 0. But when I divide by it, I end up with something that looks like this. And this function and that function, I have to see whether, what their radii of convergence are. And so this one I can write at 0, so I'm looking at the Taylor polynomial at 0, which is 1 minus x squared plus x to the fourth. This is actually a geometric series where the r that we multiply, remember geometric series, you have a starting thing and you multiply by the same thing each time to get to the next term. And this is, you're multiplying by negative x squared each time to get to here. And so our formula for how do you add a geometric series was the starting thing divided by 1 minus r. Well, 1 minus negative x squared is 1 plus x squared. So this is, in fact, a geometric series with r equal to minus x squared. And so this is the Taylor polynomial at 0. And I happen to know that this would converge from minus 1 to plus 1. X squared has to be between minus 1 and plus 1, but of course if x squared is between minus 1 and plus 1, so is x. And so it has a radius, so that's from minus 1 to plus 1, that's a length 2, but the radius from the middle out to either end is 1. The radius convergence 1. Likewise, this one right here, 1 over x plus 2, is also a sorry, it's also screwed up, so let me see if I can fix it. Yeah, that looks better. This is also a geometric series, and it's still screwed up. I think I got it now. Starting with a half, each time I'm going to multiply by negative x over 2. So a half times negative x over 2 is bx over 1/4, and a half, so then that times negative x over 2 would be positive x squared over 8, and minus x cubed over 16. This is a geometric series with the initial thing as a half, and then you're multiplying by negative x over 2. And so really there's a half on the top, and there's a 1 minus x over 2 on the bottom, 1 minus negative x over 2 on the bottom, because that was the 1 over 1 minus r. But the minus minus becomes plus, and then you multiply top and bottom by 2, and you end up with this. So this is the Taylor series for that, and I can see that x over 2, the absolute value of x over 2 has to be less than 1, right? Because the geometric series converges as long as the r is less than 1. So in this case, the r is x over 2, absolute value, right? So that means the absolute value of x has to be less than 2, which means the radius of convergence is 2. You go from -2 to +2 with 0 in the middle, okay? So this has radius of convergence 2, which tells me that whatever the solution is that I get here, when I do this would not be a simple problem, but still I could do a power series solution for this, and it would have a radius of convergence of 1 or more, right? It'd at least be 1, because the smaller of these two is 1. Okay, so the radius of convergence is at least 1. Now, one of the things I want to point out about looking at radius of convergence is that even before you've got this, before you find the Taylor polynomial for this function, there's a couple of things I look at. Well, this one is more obvious to me. This one has a vertical asymptote at x equals -2. So if I'm centering at 0, and I've got to worry about centering at 0, where am I here? And I've got a vertical asymptote over here at -2, then I'm not going to get anything greater than radius 2, because that asymptote is going to get in the way. It's going to cause discontinuity. And so I can't expect to have a solution a power series solution with an interval of convergence greater than 2, because starting at 0, I bump up against an asymptote of 2. If I had centered it over at 4, then I'd have all the way to -2, so maybe I could have a radius of 6, but I'm not centering at 4, I'm centering at 0. This one, on the other hand, is a little trickier, because this one I look at and I say 1 over 1 plus x squared. That doesn't have any vertical asymptotes. That is never equal to 0 in the denominator. However, the radius of convergence is only 1. And the radius of convergence is only 1 because of this picture right here. Now, I'll post another video with what I'm doing with coloring the complex plane. I'm looking at functions of complex variables by coloring the plane. What I need to get out of it here, this is the real axis running through here. This is the imaginary axis. The color yellow is meaning positive real numbers. So on the real axis, this function, 1 over 1 plus x squared, is always a real number. In fact, it's always a positive real number. But in the imaginary direction, particularly at x equals I and minus I, the denominator could be 0. In fact, at I and minus I, it is 0. And so this has a vertical asymptote at I and a vertical asymptote at minus I. And so with my power series going to be centered at 0, I have asymptotes not one away in the real direction, but one away in the imaginary direction. And these interval of convergence, the interval of convergence that we're talking about, actually is a disk of convergence, that in the complex plane, all of the points within radius 1, when plugged into this power series, would converge. In fact, it's absolutely convergent. This has plus and minus signs, but you could make them all pluses and it would still converge with any input from the unit disk in the complex plane centered at the origin. Okay. So the interval of convergence is actually a disk of convergence, and you can measure out to where you bump into an asymptote even out there in the complex world. So centering at 0, this one's only good for a distance of 1 until it hits that. If I had centered it out here at, let's say, 2, I believe that I plotted this from -2 to +2 in both directions. So +2 is here, right? So if I was centering the the power series for this function, the Taylor series for this function at 2, then that distance away from that intercept, that asymptote right there is, what's this, 1, this is 2, so 1 squared plus 2 squared would be 5. So the square root of 5, I would expect a radius of convergence to be the square root of 5. So that's the distance from my center to the closest asymptote. Okay. So when you're looking for radius of convergence, you can quite often just say, where am I centered, and where do I see any asymptotes? What's the closest one? That's going to be the radius of convergence for my power series centered at that point. Okay. You might want to take a look at the video for what I'm doing here. It's really cool the way I can use complex numbers to generate some really crazy pictures. So anyway, there's the stuff from this section. I think that's enough to get you through doing the homework from section 5.3.